Hello everyone, this is Carol. Welcome to my final presentation for Math 420, History and Philosophy of Mathematics. Welcome to navigate through the life stories and mathematical achievement of John Wallis with me. This is my presentation outline. I will start from some important milestones in Wallis' life. I then move on to his mathematical achievements. The third part of this presentation is on his connections to his contemporaries, and I wrap up with his legacy upon today. Before we start the storytelling, I want to invite you to pause and take a look at this portrait. The portrait of John Wallis was completed in 1701 by Sir Godfrey Kneller, a then leading portrait painter in the English court. The portrait is now part of the collection at National Portrait Gallery in London, the UK. Considering the completion year, it was certainly a portrait of the seasoned mathematician. Wallis was actually 86 years old then. The scarlet robe and the composed look convey his high reputation in England. Interestingly, such composure seems to contradict with his well-known hot temper in his numerous disputes with his contemporaries throughout his career. I also want to use this quote from the British writer and lay theologian C.S. Lewis to embark on this navigation with you, because this quote beautifully encapsulates John Wallis' contributions to mathematics and other fields in his own lifetime and beyond. So this is the quote. "For the present is the point at which time touches eternity." Certainly, the early modern England shaped his intellectual and personal lives, and vice versa. Wallis modeled the 17th century English intellectual history substantially. Let's begin our first chapter of his life story. John Wallis was regarded the most influential mathematician before Isaac Newton in the UK. He was born to a priest father in Ashford in Kent, England in 1616. Throughout his lifetime, England encountered numerous challenges. Wallis lived in a significant political moment in English history. After the prosperous reign of Queen Elizabeth I between 1558 and 1603, England experienced a tumultuous century dominated by years of civil war between 1642 and 51. The Civil War was intertwined with political drama, religious division, and threats from foreign powers. All these incidents shaped Wallis' academic career and political involvement significantly. Later in his life, the Restoration and the Glorious Revolution took place to establish the new foundation of limiting king's power and enhancing the political status of the parliament. Wallis was first exposed to mathematics, in particular to rules of arithmetic, around 1630. Even though Wallis started exploring mathematics in his teens, he didn't major in mathematics at Cambridge University. Wallis actually regarded math as a practical field for traders, merchants, seamen, carpenters, and so on. It was thus not suitable for his serious academic pursuit. These two images here show a school in Ashford, and the school was named after John Wallis. The school highlights science and math education, partially to commemorate Wallis as a famous person from this town. Now let's zoom in a bit to his formal education. On top of his early exposure to math, young Wallis studied Greek, French, Latin, logic, and music. He later majored in medicine at Cambridge University, and he completed his BA and MA degrees in 1637 and 1640, respectively. He did not engage with math seriously until 1649. The image here showcases Cambridge University in the 17th century. Wallis' serious engagement with mathematics started from his professorship, i.e., Savilian Professor of Geometry at Oxford University. He held his position until his death in 1703. Wallis' professorship at Oxford served as the evidence of political turmoil during and after the Civil War in England. The war between 1642 and 51 was featured with political division between the parliamentarians and the royalists. It is widely believed that Wallis was appointed as the replacement of several professors who had expressed sympathies toward the royalists. Wallis, on the other hand, moderately and consistently supported the revolution. Since then, he dedicated the rest of his life to numerous mathematical discoveries and inventions. The fruits of his dedication were a variety of academic writings, letters, and journal publications. Here in the background, you can see Oxford University in the 17th century. In addition to being a professor, Wallis served as a chief cryptographer for the Parliament between 1643 and 1689. Serving as a cryptographer was a highly respected profession for protecting national security. Throughout his lifetime, Wallis was close to the Puritan party, which might explain his work for deciphering for the government. He attempted to improve deciphering in the UK and resisted foreign assistance, for example, from Germany. By doing that, he hoped to protect the national security. He was also ordained as a priest for the Anglican Church, and later he composed several volumes of theological writings outside his academic pursuit. Here is an Anglican church in the 17th century in the UK. As I mentioned earlier, Wallis also worked as a cryptographer for the Parliament throughout his career. From modern perspective, cryptography seemed like a side project from Wallis' professorship. However, one can see how math and code breaking are related to one another until today. This image here is an enciphered letter from Gabriel de Luz d'Aramon, a French ambassador to the Ottoman Empire in the year of 1546. The letter was partial decipherment. From this image and Wallis' long-term involvement, it is not hard to see that code breaking has been a cross-cultural and cross-century endeavor. Let's now move on to discuss Wallis' mathematical achievements. Wallis was renowned for his outstanding mental calculation skills. He actually wrote an essay for Philosophical Transactions in 1685, stating that one can memorize better during the night. He cited his own experience for calculating the square root of 3 in head, well, up to 20 decimal places during his sleep, as evidence. In addition to his astonishing calculation skills, it is also worth noting that memory and sleep were discussed in the 17th century, much earlier than the development of neuroscience in the late 20th century. From this example, we could argue that Wallis was a pioneer in many fields indeed. Among many of his famous books on mathematics, Arithmetica Infinitorum has been considered as masterpiece. Here's a quote from Jacqueline Stedel, a late historian of mathematics, specializing in John Wallis and a translator of his books. Here's a quote. Wallis drew on ideas originally developed in France, Italy, and the Netherlands: analytic geometry and the method of indivisibility. He handled them in his own way. His writing was a crucial step towards the development of a fully fleshed integral calculus some 10 years later. Stedow's commentary highlights Wallis' position as a cross-cultural and cross-generational bridge in mathematics. Inside this book, Wallis extended from whole number to fractional exponents. As you can see from here, represented as n in this simple equation. Based on previous mathematicians' combinations of geometry and algebra, Wallis advanced the study of areas under curves via the use of fractional exponents. He also introduced this beautifully crafted formula. As you can see from here, the numerical repetition and also the involvement of pi. In another important book, Mathesis Universalis, Wallis, based on his predecessor's work on exponents, he discussed the utility of exponents. He extended the use of positive integers to rational numbers, which include negative and fractional numbers. He also introduced the symbols of infinity, of greater to or equal to, in his another book, De Sanctionibus Cognitis. So here you can see the use of negative number and fraction as exponents. In fact, it is believed that even though many ancient Greek mathematicians and philosophers contemplated on this idea of infinity, Wallis was actually the first person to consolidate and promote its use. Since then, infinity has been discussed in and outside the mathematical domain. Well, infinity also happens in popular culture, such as this famous line in the Disney film Toy Story, "To infinity and beyond." Wallis' introduction of infinity certainly has been enriching human imagination and the theorization of numbers. Let's move on a bit to another topic, the history of negative numbers and Wallis' involvement. Wallis refused the idea that negative numbers were absurd. He was usually credited as the originator of using number lines, especially to represent negative numbers as legitimate quantities. It actually took a long time for mathematicians to consolidate the definitions of negative numbers. Only until the 19th century did British mathematicians such as De Morgan and Peacock start delving into laws of arithmetics for proper definitions of negative numbers. Let's take a look at its long development. Around 200 BCE, Chinese began to use red and black rods to represent positive numbers, or profits, and negative numbers, or debts. Around 620 CE, the Indian mathematician Brahmagupta used the contrast between fortunes and debts for positive and negative numbers. Diophantus, the famous Alexandrian mathematician, on the other hand, regarded negative results as absurd ones, while he explored how to represent the unknown. Let's shift to the Middle East. Al-Khwarizmi, the father of algebra, he was influenced by Greek mathematical development, so he also regarded negative numbers as meaningless figures. Abu Wafa in the 10th century, on the other hand, represented debt with negative numbers. Interestingly, it wasn't until the 15th century that Europeans started to explore negative numbers because of translating Islamic works. And such translation later led to more investigation into solving equations in the following 2 to 3 centuries. In the 17th century, John Wallis invented the use of a number line and visualized negative numbers within the line. The invention imposed some influence on the later development of imaginary numbers and the official acceptance of negative numbers in the 19th century. Nowadays, number lines are essential in elementary and middle school math education around the world. These two images here show how ancient Chinese and Indians utilized negative numbers. So you can see these are the red and black rods. Let's think further. To understand Wallis' legacy thoroughly, one cannot ignore his influence on Isaac Newton. It is obvious that Wallis had a positive influence on Newton for his work on calculus, especially through his 1656 book, Arithmetic of Infinities. It is now known that Wallis and Newton had correspondences. It is unclear, though, if both great mathematicians met in person in their lifetime. Nevertheless, nowadays, calculus is essential for many fields: engineering, astronomy, navigation, biology, economics, music, medicine, and artificial intelligence, just to name a few. It is useful as it involves studying rates of change, which is advancement from the static geometry inherited from Greek traditions. Calculus certainly has been enriching human understanding of the world. Even though Newton and Leibniz are usually credited as the inventors of calculus, one cannot ignore Wallis' contribution to Newton's work in this long mathematical journey. Wallis' dedication to translating ancient Greek mathematical texts was evident in his lectures on Euclid's Elements at Oxford University between 1651 and 55. Delivering these lectures was part of his professorial duties. The scripts of these lectures were not published, but preserved in one of the Oxford libraries. From these well-preserved scripts, one can see Wallis' intention to include the original Greek terms and definitions from Euclid, and these terms and definitions were accompanied by Wallis' own Latin translation. He also referred to several ancient Greek and contemporary mathematicians in these lectures. These references, I would argue, highlight Wallis' sense of historicity and his intention to deliver these lectures to university students in a humanistic approach. This is the book cover of his lectures. Now let's move on to Wallis' connections to his contemporaries and other fields. The publication of Arithmetica Infinitorum in 1656 brought Wallis to the international circle of intellectual conversations and disputes. It also brought Wallis to confrontations with several French mathematicians in the next 2 decades: Fermat, Pascal, Dirichlet, and Descartes. These disputes usually took place in mathematical challenges, in letter exchanges, and critiques against one another's publications on then well-known journals. Wallis was also famous for his debates with the English philosopher Thomas Hobbes between 1659 and 79. Hobbes actually died in 79. So here you can see a comparison of these two intellectuals. Originally, these debates captured the two intellectual views on geometric questions, and Hobbes apparently failed to defend how to square the circle against Wallis' outstanding mathematical reasoning. Nevertheless, the debates later included politics, church governance, and natural philosophy, and Wallis failed to ruin Hobbes' authority in political and natural philosophy. Wallis also had a reputation of sending his new publications to friends and acquaintances for gaining fame as an outstanding intellectual. When his 3-volume opera Mathematica was published in the 1690s, he sent out copies as usual. Then famous diarist Samuel Pepys was impressed by Wallis' lifelong mathematical achievement. So Pepys initiated the commission of Kneller's portrait of Wallis. That was the portrait that we saw at the beginning of this presentation. So what's the point of these disputes? Scholars of John Wallis usually interpret these disputes with his contemporaries as his nationalistic defense for his English pride, especially against the French mathematicians. Some even believe that they represent his strong anti-Catholicism, which was also evident in his theological writings. Some others, on the other hand, read them simply as his self-arrogance. Well, personally, I think it's a mixture of these three elements. It's really hard to differentiate one from another. Now, let's turn to Wallis' involvement in the foundation of the Royal Society. Wallis was one of the founding figures. He started meeting the contemporary intellectuals for discussing natural philosophy and natural sciences in the 1640s. Wallis was also active in publishing a wide range of topics, in fact, over 60 journal articles in Philosophical Transactions, as the Royal Society came into existence in late 1660. Philosophical Transactions has been the official journal publication of the Royal Society since its beginning. Forwarding into 2021, one can still see that Wallis' essays have been well preserved physically and digitally in the Royal Society. Such preservation is an official recognition of his intellectual involvement. This image here is the facade of the Royal Society nowadays. It was the first scientific institution in the world, and it still has great reputation nowadays around the world. In addition to his mathematical and scientific contributions, Wallis has been reckoned as a significant scholar of English grammar, mainly for the publication of this book, Grammatica Lingua Anglicana, in the year 1653. It was actually right in the midst of his writing peak. Wallis distinguished himself from then common approach through the lens of Latin models. Instead, he used an empirical approach to trace how English phonetics and grammar had been evolving. Such an empirical approach was influenced by the growing scientific movement in the 17th century in England and Europe. So here is an image of 2 pages from this book. Let's now turn to his theological approach. Wallis was famous for his lifelong anti-Catholicism, and such position led to his political, scientific, and mathematical decisions at times. More precisely, his anti-Catholicism was more towards the Pope, so perhaps it's better to be phrased as anti-papism. Here are two examples for us to explore his anti-papist tendency. In 1677, Wallis produced a more exact translation of a British biblical commentator, Francis Potter's interpretation of number 666. With a focus on the book of Revelation, Potter explored 144 as God's number and 666 as the number of beast. He contended that the square roots of 144 is 12, which is a usually divine biblical reference. On the other hand, the approximate square root of 666 is 25, which is a symbol of sins and especially associated with the Roman Church. It is very strange that Wallis would endorse this book because he had no interest in numerology and exegesis in his long career. The only possible explanation for his endorsement is Potter's obvious attack on the Roman Church, which resonate with Wallis' own anti-papism. Another incident demonstrates Wallis' political influence over English politics later in his career. When England was deciding to use the Gregorian calendar for its better astronomical precision than the previously accepted Julian calendar, Wallis was concerned that Catholic power would dominate England, for the Gregorian calendar was supported by then Pope Gregory VIII. The change of calendar was first proposed in 1700, 3 years right before Wallis' death, but England did not change the calendar until 1752. Again, one should question if Wallis was aware of the astronomical inaccuracy of the Julian calendar, as objective as a mathematician or scientist. Well, it can be challenging for one to initiate this philosophical contemplation. Stephen Shapin, a 20th century American sociologist of science, might provide some insights for us. He has this quote: "Science happens within, not outside of, historical time. That it has a deep historicity. Science similarly belongs to a place, that it bears the marks of the places where it is produced, a spatially grounded phenomenon." Reading upon Shapin's sociological insights, I would conclude that Wallis' mathematical and scientific writings were no exception, and his theological worldview might be intertwined with his scientific training. Now let's move on a bit. In 2014, a book titled John Wallis' Writings on Music was published. This publication has been enriching the growing contemporary scholarship on Wallis. It centers on this essay: the harmonics of the ancients compared with today's appendix to Ptolemy's harmonics. So it was published by Wallis in 1682. The central piece is accompanied by Wallis' private letters with then intellectuals between the 1660s and the 90s. These letters reveal Wallis' strong theoretical interest to explain musical harmony mathematically. One can also see his dedication to translating ancient Greek classics during his Oxford professorship. Wallis is also recognized as the first successful teacher of the deaf. He studied how to form sounds and tongue structure. Later on, linguists confirmed that Wallis' method initiated a new phase in linguistic science. This story was also documented in this book, Teaching Language to a Boy Born Deaf, the Popham Notebook, as you can see from here. Now we come to the final part of my presentation. Let's move forward to Wallis' legacy in the 21st century. The recent scholarly surge of Wallis' research originated from a workshop at the University of Toronto in Canada in 2016 as a commemoration of Wallis' 400th birthday. In the first 2 decades of the 21st century, several publications enhanced academic and public understanding of this multimath. For example, the Correspondence of John Wallis, Volumes 1 to 4, John Wallis, Writings on Music, and this one, Distinctions of Reason and Reasonable Distinctions, the Academic Life of John Wallis. Nowadays, Wallis is remembered for numerous developing mathematical ideas, including infinitesimals, which later heavily influenced differential and integral calculus, as well as astronomy and theoretical physics. In this presentation, I demonstrated how the life trajectory of John Wallis enriched mathematical development and other fields in England and beyond. His life might be merely a short moment compared to the thousands of years in the history of mathematics, but certainly his name has been continuously enlightening numerous later mathematicians, math educators like myself, and learners. These are my image references. These are my overall references for this presentation. Well, I hope you enjoyed this presentation. If you're interested in reading the paper version of this presentation, you can find the link in the video description. Thank you for listening. Bye-bye.